Okay, so in this first example of pressure versus temperature, I want to remind you, as I do in every podcast of these examples, of what the relationship between pressure and temperature is. So the pressure and temperature are directly proportional. Again, hopefully you've watched by now the pressure versus volume, and you've seen the pressure and volume are the only ones that are inverse, meaning they're opposites. So pressure and temperature change in the same direction. If the pressure goes up, the temperature will go up, and vice versa. So what you'll see in a lot of these types of problems actually are, they are much more word problem based. So I'm sorry, where the other one basically just told you the numbers outright, this is now a word problem where it's going to give you like a story behind the problem. So let's look at this. And the reason they give it to you is they want to make sure you know that the volume is constant as you go through it. So argon gas is sealed in a metal canister at a pressure of 1 atmosphere and a temperature of 20 degrees Celsius. Over the next hour, the temperature is raised to 50 degrees Celsius. What will be the resulting pressure after this time? Is the time important? Absolutely not. Ignore all that superfluous information, meaning extra information. Okay, so let's just focus in on what we need to solve this problem. So, well, we know that when we did pressure and volume, the P1s and the V1s and all that stuff were opposite to each other. And when we did volume and temperature, that they were on the same side. So since volume and temperature are directly proportional and pressure and temperature are directly proportional, the formula for this is going to be very similar. So we're going to get P1 over P2 equals T1 over T2. Now, just like in the previous problems, I'm going to list off what I know. I know my P1 is 1.0 ATMs. Where did that little red line come from? Okay, how do I know? It's right there. My P2 is what I'm solving for. How do I know that? It says, what will be the pressure? Okay, so our T1 is 20 degrees Celsius because that is what's connected to the 1 atmosphere. 20 degrees Celsius. But as we saw previously, we never leave it as Celsius. We always put it as Kelvins. So just as a reminder, the way we get to Kelvins is we add 273. Why? Because it's a constant. It's a perfect calculation. Again, if in case you didn't watch the volume versus temperature, the Kelvin is an absolute scale, meaning it has no negative values. That's important in problems like this because if we had a negative temperature, then we'd have a negative pressure, and that would result in a vacuum, and that's just not possible. And in actuality, a vacuum is not negative pressure, it's zero pressure. So you can't have negative pressures, you can't have negative volumes, so we have to use a scale that allows for no negatives, and that's Kelvins. And the way to get to Kelvins is you just take your degrees Celsius and you add 273 every single time. So I take my 20 degrees Celsius and I add 273, which gives me 293 Kelvins. T2 is the other temperature that's here. 50 degrees Celsius plus 273, and that's going to give us 323 Kelvins. Okay? Now that I've listed off everything, I'm just going to plug it right into my formula. Where does that little line keep showing up from? Okay, 1 atmosphere over, holy crow, over P2 is equal to T1, which is 293, over T2, which is 323, and my P2 will be, and again, I'm going to cross multiply. So whip out the calc. Here he comes to save the day. Okay, so I'm going to cross multiply. So I'm going to take my P1 and multiply it by my T2. So I'm going to take 1.0 times 323 equals, obviously that's 323, divided by the thing that's multiplied by my variable, which is the 293. And I hit enter, and I get 1.10. ATM. Okay, now, does my answer make sense? You're going to get sick and tired of me saying that, but I'm going to ask it every single time. Does my answer make sense? Well, let's look at the problem. We know again that pressure and temperature are directly proportional, meaning as one goes up, the other goes up. Well, our temperature went up. So if our temperature went up, our pressure went up. So our pressure should go up. Did our pressure go up? Yes, it did. Now you might say to me, Mr. Siegel, but wait a second. It went from 20 to 50, which is more than doubled. Why did the volume only change by 0.1? Remember that it's not the Celsius that matters, it's the kelvins that matter. And if you notice, the kelvins only changed by 30. That's not a real big difference when you're talking about something that's in the hundreds. So technically it's about a 10% change. And if you notice that the pressure changed by about 10%. And that's how we know that our answer does actually make sense, okay? So please make sure that when you get to any one of the ends of these problems, you ask yourself, does my answer make sense? In this case, since temperature went up, our pressure should go up. It did, and our answer does make sense.